Hello everyone. So in today's video, we are going to go over this paper, Transformer Feed-Forward Layers are Key Value Memories by Jiva, Schuster, Barand and Levy. I'm really sorry if I mispronounced any of those names. Also, I haven't read this paper before and this is, I believe, one a bit more technically involved. So let's go right through it. So I might be googling stuff in between. This would just be how I typically read papers. So the abstract. Oh, okay. Let me just check if I'm even recording right. Would be pretty bad if I am not. Yeah, it's recording. Okay, so yeah. So the abstract feed-forward layers constitute two-thirds of a transformer model's parameters, yet their role in the network remains underexplored. So by feed-forward layers, these are just the feed-forward layers which are present within the encoders and give two-thirds of the total parameters. So in this work, they show that feed-forward layers in transformer-based language models operate as key value memories, where the key correlates with textual patterns in the training examples, and each value indicates a distribution over the output vocabulary. So this is pretty interesting. Essentially, what they're trying to say is we figured out what these MLPs are doing. So some people have tried to uh, corrupt those MLPs or tried to find ways to make the attention and MLP computation parallel. I believe GPT-J does that. So they're basically trying to identify what these MLPs are doing. So their experiments show that the learned patterns are human interpretable, and the lower layers tend to capture shallow patterns while the upper layers learn more semantic ones. So this is also interesting. This is something which you would expect from, or if you've studied CNNs, CNNs do this stuff, right? CNNs, the earlier layers in the CNNs are said to be capturing high level features like edges or uh, just boundaries, and the lower and the deeper layers, the layers towards the final softmax layer, they are supposedly capturing the more nuanced semantic features. So the value complement the key's input pattern by inducing output distributions that concentrate probability mass on tokens likely to appear immediately after each pattern, particularly in the upper layers. So of course this makes more sense in the upper layers because in the upper layers you're going to be finally decoding, right? Finally, we demonstrate that the output of a feed-forward layer is a composition of its memories, which is subsequently refined throughout the model's layers via residual connection to produce the final output distribution. So, a composition of its memories. I'm not quite sure what they mean by that. Maybe as we go through the paper, we'll understand this better. But what I can understand from this statement is that the residual connections are sort of taking information and not taking all of the information, but some information. But how would that work out since residual connections blindly take everything? Maybe reading the paper would answer those questions, but the abstract itself is quite enticing. So, the introduction, I'm not going to explain all the generic things because I assume you're all familiar with transformers if you're watching this video. Transformer based language models are at the core of the state of the art NLP, yeah, largely due to the success of self attention. While much literature has been devoted to analyzing the function of self attention layers, they account for only a third of the typical transformer parameters. So you have 4D square per layer, where D is the model's hidden dimension. D square because you have attention between every token and every other token. Most of the parameter budget is spent on point-wise feed-forward layers, which are 8D square per layer. Yet their role remains underexplored. So what if so is the function of the feed-forward layers in a transformer language model. So perfectly explaining why this work is relevant. We show that feed-forward layers emulate neural memories. Okay, where the first parameter matrix in the layer corresponds to keys and the second corresponds to values. So figure 1 shows how the keys, so the first parameter matrix, which acts like the input to produce coefficients, which are then used to compute a weighted sum of the values as the output. While the theoretical similarity between feed-forward layer and key value memories has previously been suggested by Shubatar et al. 2019, we take this observation one step forward further and analyze the memories that the feed-forward layers store. So let us just go over this part again. Keys, which is the first parameter matrix, is the key for them, which takes the input and produces coefficients. Okay, and then these are used to compute a weighted sum of the values, which is second parameter matrix, and gives out the result. So if we zoom in on this diagram, you can see you have this input. This goes into the network. You get a bunch of keys. You get some weights. These weights are multiplied by the values, and then you get a distribution of some sort, which I guess is the distribution which we were talking about. And then all of that comes together to get your final output token. So an illustration of how a feed-forward layer emulates a key-value memory. So input vector here, x5 are multiplied by keys to produce memory coefficients. So memory coefficient is how much, I guess, weightage you put to that particular memory, which like it is zero point 0.2 for value 1, which then weighs distributions over the output vocabulary stored. The feed-forward layer's output is thus the weighted sum of its values. Right. Right. So we find that each key correlates with a specific set of human interpretable input patterns, such as engrams or semantic topics. And for each example, so for example, K2 in figure 1 is triggered by the inputs that describe a period of time and ends with a. Okay, so what's K2 here? Okay, so K2 is getting a very high weight, as you can see, a weight of 1.5, while others are like zero point 0.2 and 0. So it is being triggered by the input, which is talking about some period of time, because you can see it's a time like statement and it's ending with a. Simultaneously, we observe that each value can induce a distribution over the output vocabulary. Each value can induce a distribution over the output vocabulary, and that this distribution correlates with the next token distribution of the corresponding keys in the upper layer of the model. So in this example, the corresponding value V2 describes a distribution that puts its probability mass on the value while. So again, going back here, this V2 was a distribution which was putting its probability mass on the value while, and then this high weightage given to this token, this distribution further enhances its presence. Lastly, we analyze how the language model as a whole composes its final prediction from individual memories. We observe that each layer combines hundreds of active memories, creating a distribution that is qualitatively different for each of its component memory values. Okay, so each layer combines hundreds of active memories, creating a distribution that is qualitatively different from each of its component memory values. So it's sort of taking everything, right? That is why it's different from everything inside it. Meanwhile, the residual connections between layers act as a refinement mechanism, greatly tuning the prediction on each layer while retaining some of the residual information. All right. So they gently tune the prediction at each layer while retaining the residual information. So we'll be getting more into detail for each of these things, but right now we're just getting a high level idea. In conclusion, the work sheds light on the function of feed-forward layer in transformer-based language models, and they show that feed-forward layers act as pattern detectors over the input across all layers, and that the final output distribution is gradually constructed in a bottom-up fashion. So their experiments are linked here. The GitHub is given. Right. So I guess this is still a part of the related work section. No, not a part of the related work section. This is a new section altogether. So feed forward layers as unnormalized key value memories. So feed forward layers, a transformer layer model by Vaswani et al. Is made of intertwined self-attention and feed forward layers, each Feed-forward layer is a position-wise function processing each input vector independently. That is why it's known as point-wise feed-forward network. I hope you're familiar with all of this. So let X belonging to the d-dimensional space be a vector corresponding to some input text prefix. We can express the feed-forward layer as following. So you take the input X, you multiply it with the key matrix, and then again with the value matrix. So this is the key and value which they have defined up here, I believe. This is not the key and value which you might think in terms of, say, attention. So key and value are just parameter matrices, and F is a non-linearity such as ReLU. Again, neural memory. A neural memory consists of DM key value pairs, which we call memories. Okay, each key is represented by a d-dimensional vector ki belonging to Rd, and together form the parameter matrix dm cross R belonging to dm cross D. So essentially what they're trying to say is each column in R is a key. Likewise, you define the value vector as in the same space. So given an input vector x belonging to the d-dimensional real space, we compute a distribution over the keys and use it to compute the expected value. So you get this distribution over the keys, and then you scale the values with that. And so by converting this into terms which are more familiar, you get this formulation. So I believe till this point everything is something which you've seen in some other form just being reformulated. So feed-forward layers emulate neural memory. So if you compare equation 1 and equation 2, so equation 1 is this equation. Um, sorry. Yeah, equation 1 and equation 2, they do look quite similar, don't they? So the only difference is that the neural memory uses softmax, while the canonical transformer does not use a normalizing function in the feed-forward layer. Yeah. So the hidden dimension dm is essentially the number of memories in the layer, and the activation m, commonly referred to as the hidden layer, is a vector containing an unnormalized non-negative coefficient for each memory. Right. So let's just break this down point by point. So the hidden dimension dm is essentially the number of memories in the layer. So if you have a matrix and the dimensions of the matrix are dm cross d, you have dm number of keys. And then the activation m, which is f of x into k transpose. So this value, this is referred to as the hidden layer because you haven't yet multiplied it by the value, right? So this is the fan-in matrix sort of thing. So you have such a setup. First you go into a hidden dimensional space, and then you go out of that. So this part, and this is known as the hidden layer. And if you compare it to a neural memory, it is similar to a vector containing an unnormalized non-negative coefficient for each memory, because you'll have one coefficient for each of the dm memory vectors, and we refer to each mi as a memory coefficient for the ith memory cell. So I believe so far it should be pretty clear if I'm doing a good job explaining it. And I'm not really sure if I can explain it much better than this because I'm also reading this for the very first time. So Sukhbadar et al. 2019 make an analogous observation and incorporate the parameters of the feed-forward layer as persistent memory cells in the self-attention layers. Okay, so I'm not sure what they mean by that, but I guess they'll go into this. So while this reparameterization works in practice, the experiment does not tell us much about the role of the feed-forward layers in the canonical transformer. If transformer feed-forward layers are indeed key value memories, then what memory do they store? Okay, so I guess what Sukhbadar et al. Did was They took the parameters of the feed-forward layer and removed the feed-forward layer altogether. And they added that as a persistent memory cell in a self-attention layer. But I might be wrong, so I will need to go over this work maybe in a future video. So we conjecture that each key vector ki captures a particular pattern or set of patterns in the input sequence, and that its corresponding value vector represents the distribution of tokens that follow the set pattern. So if you have a pattern, so in more simpler terms, you must have read hundreds of sentences, right? Hundreds is an understatement. I guess hundreds or thousands of sentences. So at some point, you know, right, if these words are coming up, it's highly likely that these set of words are going to follow. So maybe the sentence is I am, the prefix is I am, and then you are able to guess that I am a seems like an obvious continuation. Okay, so I'll take a break right here for some water and I'll be right back. Yeah, so I'm back. Yeah, probably wouldn't even have felt it if I didn't mention it explicitly. Right. So keys capture input patterns, the third section. We posit that the key vectors k in a feed-forward layer act as pattern detectors over the input sequence, where each individual key corresponds to a specific pattern over the input prefix. So to test our claim, we analyze the keys of a trained language model's feed-forward layer. So we first retrieve the training example, so the prefixes of a sentence most associated with a given key, that is the input text where the memory coefficient is highest. So this is the first step. Then we ask humans to identify patterns within the retrieved examples. For almost every ki in our sample, a small set of well-defined patterns recognizable by humans cover uh, almost everything associated with the keys. So this looks very interesting. Uh, this is the experimental setup. We conduct an experiment over the language model of Bevisky and Ollie, a 16-layer transformer model trained on Wikitext 103. This model defines D1024, DM4096 and has a total of DM into 16 potential keys to analyze. We randomly sample 10 keys per layer. So they have 160 keys. Then retrieving trigger examples, we assume that the patterns stored in memory cells originate from the examples the model was trained on. This makes sense. Therefore, given a key KIL that corresponds to the ith hidden dimension of the lth feed-forward layer, we compute the memory coefficient for every prefix of every sentence from the wiki text's training set. Okay, so for example, for the hypothetical sentence I love dogs, we'll compute three coefficients for the prefix I love, and I love dogs. Then we retrieve the top T trigger examples, that is the T prefixes whose representation at layer L yielded the highest inner product with Ki. Alright. So what they're trying to do is they're trying to find which pattern triggers which dimension in which layer, right? So they have a particular example, so they're doing this for every sentence in the training set. So suppose they have the example I love dogs, they'll find every possible prefix which can be generated from this. So it can be I love, and I love dogs. Then they take this, they like pass it through the network, and they compute the memory coefficient for the prefix. So the memory coefficient, as we saw, was just this. If we go back to that equation, this equation 1 can be represented as this in terms of particular columns and rows, right? So this is the memory coefficient for that particular sample, for that prefix, and then they compare this prefix and the top T triggering examples, that is the three prefixes whose representation at layer L yields the highest inner product, is what they choose. So analyzing the patterns, they take human experts, so NLP graduate students, because of course you need linguistic patterns, right? You can't just use random people off the street. And Ask them to identify repetitive patterns that occur in at least three prefixes, which would strongly indicate a connection to the key, as this would be unlikely if the sentences were drawn at random. And describe each recognizable pattern and classify each recognizable pattern as shallow or semantic. So either they're just picking up n-grams or picking up some topic. Each key and its corresponding top 25 prefixes were annotated by one expert. To assure that every pattern is grounded in at least three prefixes, we instruct the experts to specify for each of the top 25 prefixes which patterns it contains. So you have uh, a key and its top 25 prefixes, and then for to assure that every pattern is grounded in at least three prefixes, they ask the experts to annotate. So for the top 25 prefixes, you want to find which pattern it contains. So a pattern can also have multiple, a prefix can also have multiple patterns. And table 1 contains this. So let's have a look. So this is the 449th. Let's just have a look. This is the 449 dimension of the first layer because the superscript is 1, and you can see it ends with substitute. So at the meeting, Elton said that for artistic reasons there could be no substitute, so everything is ending with substitutes. Then the 2, 4, 5, sixth new hidden dimension in the sixth layer and ending with bases. Then you have some deeper layers capturing some more significant relation. So part of relation is captured here in these sentences. Then you have time range based sentences, and then you have TV show based things. So you can see they've sort of made it observable using this sort of analysis. So the results: memories are associated with human recognizable patterns. Experts were able to identify at least one pattern for every key, with an average of 3.6 identified patterns per key. Furthermore, the vast majority of retrieved prefixes were associated with at least one identified pattern. Thus, the top examples triggering each key share clear patterns that humans can recognize. So, let's have a look at this plot. Breakdown of the labels experts assigned to trigger examples in each layer. Some examples were not associated with any pattern, so they're not covered. So you can see in layer 1 you have more shallow patterns and less semantic patterns, and you can see this value going down and this going up, which is what a lot of deep language models hypothesize, right? That the earlier layers are more important for capturing high level features. Then shallow layers detect shallow patterns. So comparing the amount of prefixes associated with shallow patterns and semantic patterns, the lower layers are dominated by shallow patterns, uh, often with prefixes that share the last word. In contrast, the upper layers are characterized by more semantic patterns. This observation corroborates recent findings that lower layers in deep contextualized models encode shallow semantic features. To further test this hypothesis, we sample 1600 random keys, so 100 keys per layer, and apply local modifications on to the top 50 trigger examples of every key. Specifically, we remove either the first, last, or random token from the input and measure how this mutation affects the memory coefficient. Figure 3 shows the model considers the end of an example as more salient than the beginning for predicting the next token. In upper layers, removing the last token has less impact, supporting a conclusion that they are not using shallow patterns. So you can see uh, for the upper layers, so the later layers, so this is less. Okay, sorry, this is not what this key means. I'm sorry. These are the layers, right? So for the 16th layer, removing the last token has much less impact than removing it for the first layer. All right, so value represent distributions. After establishing that keys capture patterns in training examples, we turn to analyze the information stored in their corresponding values. Alright, so now we do have a clear idea of what the keys are storing. So now let's look at what the values are storing. We show that each value VIL, so the value of lth hidden neuron in the ith layer, can be viewed as a distribution over the output vocabulary and demonstrate that this distribution complements the patterns in the corresponding keys in the model's upper layers. So how do you cast it as a distribution, right? We begin by converting each value vector into a probability distribution by multiplying it by the output embedding matrix E and applying a softmax. All right. So this gives us the probability distribution. So this is uncalibrated since the value vector is typically multiplied by the input dependent memory coefficient MIL, but we haven't yet done that. So uh, we haven't yet calibrated it based on the memory values, which would change the skewness of the output distribution. That said, the ranking induced by PIL is invariant to the coefficient and can still be examined. This conversion assumes naively that all model layers operate in the same embedding space. So this is the output embedding matrix which we're talking about. Uh, Also, in practice, they're using adaptive softmax. So value predictions follow key patterns in upper layers. So what does this mean? For each layer L and memory dimension I, we compare the top rank token according to VIL. So you just take the argmax over the entire vocabulary to the next token WIL. In the top one trigger example, according to KIL, the example whose memory coefficient for KIL is the highest. So what they're trying to do is they're trying to look back into the training sentence, find the next token which should occur according to that training sentence whose pattern is captured. They're also, of course, taking the pattern, the training sample which had the highest trigger, and see if this is the case, if that particular token is being given the highest probability mass. So figure 4 shows the agreement rate. That is the fraction of memory cells where the value's top prediction matches the key's top trigger example. It can be seen that the agreement rate is close to zero in the lower layers but rises from layer 1. 11. The agreement rate quickly rises until 3.5%, showing higher agreement between keys and values on the identity of the top rank token. Importantly, this value in order is orders of magnitude higher than the random token prediction from the vocabulary, which would produce a far lower agreement of 4e minus 4, showing that upper layer memories manifest non-trivial predictive powers. Alright, so again, as you can see, this is how you would assume your models to be, right? The last layers are getting more semantic information, I guess. So they are now able to gather the information from every other layer in the past to make an informed choice to predict the next token. Next, we take the top token of KIL's top one trigger example WIL and find where it ranks in the value vector's probability distribution PIL. The figure 5 shows the rank of the next token of a trigger example increases to the layer, meaning that WIL tends to get higher probability in the upper layers. Uh, let's try to understand this once again. We take the next token of KIL's top one trigger example and find where it ranks in the value vector distribution. Figure 5 shows that rank of the next token of the trigger example increases throughout the layers, meaning that WIL tends to get higher probability in the upper layers. Um, this plot is a bit confusing to me. What does rank distribution here mean? According to the ranking induced by the value, we cut the tail of the distribution which stretches up to the vocabulary size. So of course, then they can't show everything, but let's try reading this again. We take the next token of KI's top one trigger example WIL and find where it ranks in the value vectors distribution. So we are trying to find not just the word to be. So right now, if we look back here, we are uh, what were we doing here? For each layer L in memory distribution I, we compare the top rank token to the next token in the top one trigger example. So here also we were taking WIL and seeing in how many cases does this match. Next, we take the next token WIL again and find where it ranks in the value vectors distribution. So right now this was the key vector. Uh, was this? No, this wasn't the key vector. This was just the argmax over the probability distribution, which was computed using the value vector again. Maybe we'll get back to this at a later stage. Detecting predictive values. To examine if we can automatically detect values with high agreement rate, we analyze the probability of the value's top prediction. Figure 6 shows that although these distributions are not calibrated, distributions with higher maximum probabilities are more likely to agree with the key stop trigger example. We then take the 100 values with highest probability across all layers and dimensions. Of course, most of them would be in the upper layers. And for each value, analyze the top 50 trigger examples. We find that in almost half of the values, there's at least one trigger example that agrees with the value's top prediction. So these examples are there in table 2. So sorry, these words are able to capture from these words are what the trigger example uses. So this is uh, talking about the predictive values. Then discussion. When viewed as distribution over the output vocabulary, values in the upper layer tend to assign higher probability to the next token uh, of example triggering a corresponding key. This suggests that memory cells often store information on how to directly predict the output from the input. Conversely, the lower layers do not exhibit such patterns. A possible explanation is that the lower layer do not operate in the same embedding space, and therefore projecting values onto the vocabulary using the output embedding does not produce distribution that follows the trigger example. And this is a valid reason because they are layers apart, right? The layers which are closer, of course, should have more related, um, what do you call that? More related embedding space. However, our results imply that some intermediate layers do operate in the same space, which in itself is non-trivial. And this they do not explore more. They say that future works can look into this. And looking at the predicted probability and agreement rate between the top rank token and the next token as a function of the maximum probability assigned by the value vector. So you can see that probabilities are high for agreement rates in many cases. So these values might look very low, right? But in fact, you have a distribution over a quarter of a million tokens, I believe. So these values are pretty high. Aggregating memories. So far, our discussion has been about a single memory cell. So how does this information from multiple cells in multiple layers aggregate to form a model wide prediction? We show that every feed-forward layer combines multiple memories to produce a distribution that is qualitatively different from each of its component memories value distribution. These layer-wise distributions are then combined by residual connections in a refinement process, where each feed-forward layer updates the residual distribution to finally form the model's output. All right. So they show that every feed-forward layer combines multiple memories to produce a distribution that is qualitatively different from each of its component memory distributions. These layer-wise distributions are then combined by residual connections because they are sort of they're like highways, right? And they can uninterruptedly flow, and this forms our model's output. So let's look at intra-layer memory composition. The feed-forward layer output can be defined as sum of value vectors plus a bias term. So this right here. In each value vector contains information about the target token distribution. How is this information aggregated into a single output distribution? To find out, we analyze the behavior of 4,000 randomly sampled prefixes. Here, the validation set is used rather than the training set to find trigger examples, since we are trying to characterize the model behavior at inference time, not find the example it memorizes during training time. We first measure the fraction of active memory cells with non-zero coefficient. Figure 7 shows a typical example with triggers hundreds of memories. Okay, so a typical example triggers hundreds of memories, but the majority of cells remain inactive. Interestingly, the number of active memories drops towards layer 10, which is the layer in which semantic patterns become more prevalent. So, since you have so many hidden vectors, they might be capturing some engram feature, but towards the later layers, you are looking at more dips because now semantic features are more specific. While there are cases where a single memory cell dominates the output of a layer, the majority of outputs are clearly compositional. We count the number of instances where the feed-forward layer's top prediction is different from all the memory's top prediction. Formally, we get this denotion as they want to find because they what they're hypothesizing is that the key that triggered can find the next token right in the embedding space. So this is what that would formally be represented as. And this is a shorthand for the top prediction from the vocabulary distribution induced by the vector h, and compute the number of examples where this does not hold. Figure 8 shows that for any layer in the network, the layer's final prediction is different than every one of its memory prediction, at least 68% of the examples. Even in the upper layer where the memory values are more correlated with the output phase, the layer level prediction is typically not the result of a single dominant memory cell but a composition of many memories. So they're saying that you cannot just use one key which is one memory which is more polarizing towards the output, but you're getting some output based on everything. We further analyze that where at least one memory cell agrees with the layer prediction, find that in 60% of the example, the target token is a common stop word in the vocabulary. So in this case, there are high agreements. In 43% of the cases, the input prefix has less than 5 tokens. This suggests that very common patterns in training data can be cached, but they do since they do not require any compositionality. And finally, interlayer prediction refinement. While a single feed-forward layer composes its memory in parallel, a multi-layer model uses a residual connection to sequentially compose predictions. So you have layer normalization, then a feed-forward layer, and then your residual connection. So we hypothesize that the model uses sequential composition apparatus as a mean to refine its prediction from layer to layer, often deciding that the prediction will be at least one of the lowest layers. To test our hypothesis, we first measure how often the probability distribution induced by the residual vector RL matches the model's final output OL. So this is again a similar formulation. Figure 9 shows that roughly a third of the model's predictions are determined in the bottom few layers. This grows rapidly from layer 10 onwards, implying that majority of hard decisions occur just before the final layer. Because of course the final layers have more information as well. Of course, also, I believe we forgot to go over this plot. This plot is nothing, just showing that in how many cases the final prediction is different from the prediction of all of its memories. So again, this is very high, showing that no one memory can be trusted. We also measure the probability mass P that each layer's residual vector assigns to the model's final prediction. So figure 10 shows a similar trend but emphasizes that it is not only the top prediction's identity that is refined as we progress, it is also the model's confidence in its decision. So again, the probability is also increasing. To better understand how the refinement process works, we measure how often the residual stop prediction changes following its interaction with the feed-forward layer. So this stops happening, and whether this change results from the top feed-forward layer overriding the residual or from a composition. Figure 11 shows a breakdown of different cases per layer. In the vast majority of examples, the residual stop prediction ends up being the model's prediction. In most of these cases, the feed-forward layer predicts something different. Perhaps surprisingly, when the residual's prediction does change, it rarely changes in the feed-forward layer. Instead, we observe that composing the residual distribution with that of the feed-forward layer produces a compromised prediction which is equal to neither. This behavior is similar to intralayer composition. A similar conjecture is to intralayer composition again inside the layer, combining many memories takes away the predictions of all the memories and gives a new prediction altogether. A possible conjecture is that feed-forward layer act as an elimination mechanism to veto the top prediction and thus shift probability mass towards the other candidate prediction. Finally, we manually analyze 100 random cases where the feed-forward layer modifies the residual example. We find that in most cases, the 66 examples, output changes to a semantically distinct word, and in the rest of the cases, the feed-forward layer output shifts the residual prediction to a related word. This suggests that feed-forward layer tune the residual prediction at varying granularity, even in the last layer of the model. Again, related works. So, considerable attention has been done to demystifying the operation of NLP models. An extensive line of work targeted neuron functionality, in general, extracting the properties the neuron and subset of neuron capture, regardless of the model architecture neuron's position. Uh, Jacobi et al. Analyzed CNN architecture in text classification showed that they extract key n-grams from the input. The study of transformer architecture has focused on self-attention and on inter-layer differences. Previous work has also highlighted the importance of feed-forward layer. Still to this date, this role remained unexplored, which they did. Also related are interpretability method that explain predictions. However, our focus is entirely different. We do not interpret individual predictions but aim to understand the mechanism of transformers, characterizing the functionality of memory cells based on examples that trigger maximal activations has been used previously in NLP. So discussions and conclusions. So yeah, understanding how and why transformers work is crucial, right? Feed-forward layers account for most of the parameters, but less is known. In this work, we propose the key value store memory feed-forward layers emulate key value memories and provide a set of experiments. So keys are correlated with human interpretable patterns, value mostly in the model's upper layer induced distributions or the output vocabulary that correlates with the next token distribution. And the model's output is formed by a creation of this distribution to form whereby they are first composed to form individual layer outputs and then refined through the model layer using residual connection. So some important future research directions are layer embedding space. We observe a correlation between the value distribution of the output vocabulary and key patterns that increases from lower to upper layer. Is this because the layer's output space transforms across layer? If so, how? We know that this possible transformation cannot be explained solely by the function of feed-forward layers. If the model only does a series of key value lookups and value distribution aggregation via weighted addition, then a single unifying embedding space would appear more natural. Thus, the transformation might have to do with the interplay between feed-forward layers and self-attention layers, right? That all makes a lot of sense. Beyond language modeling, so again, you can also focus on other tasks beyond language modeling. So we expect a qualitative empirical observation to hold across diverse settings, and in practical implication, a better understanding of feed-forward layers could help in interpretability methods by automating the pattern identification process as they could facilitate white box membership inference. And studying cases where a correct pattern is identified but then suppressed during aggregation might guide architectural novelty. So you might want to then highlight back those things. Thus, by illuminating the role of feed-forward layers, we get a better understanding of the inner working, and then they thank the people and the uh, associations which have supported them. So overall, this was a great paper, uh, and they've provided some more analysis towards the end. And uh, I would be going through the code, but not in this video. Uh, Not in any video for that matter. That would I would just be playing around maybe in the future. But this was a really great read, and hope you guys enjoyed it as well. So I'll catch you again in the future. And sorry for the occasionally delayed or missing updates or uploads. I've been busy due to college, but I'll probably be a bit more active this month since I'm on my vacations. So thank you guys for tuning in. Hope to see you again next time as well.